Okay, good morning. So let us go to the next chapter. Most part of this lecture will be a recap from Math 3C, but of course we will complete it today according to the knowledge that we gained for derivatives in the previous chapter. Okay, so if you see so far, we have this table that we completed during the last last lectures. So these are the functions that we know more or less in this course, and then we learn how to find the derivatives of those functions. And if you remember, the last one was tangent, but because sine, cosine, and tangents are all trigonometric functions, I wrote them together. And then we also have some generic rules that you know how to differentiate if I multiply a constant by a function, how I can differentiate if I add two functions. And then we also learned about the product rule and the quotient rule this year, and we have these rules. And of course, on top of all these rules, we have the chain rule. Yes? Here, I want to do the other way around. For the time being, you need to consider it just as a mathematical curiosity or a game. Yes? So it means that I give you somehow a function which I say this is the derivative of a function, and I want you to find the original function. Yes? So that is not called original function in the terminology that we want to talk about. It's called a primitive function. Yes? So a primitive function of a function is a function whose derivative is equal to that function. So that the process is reversed. Yes? So the point is that I give you the right column and I ask you to find the left column. But of course, if I give you exactly those, the answers are already there. So yes, if I give you 0 and I ask you what is the original form of your function, you definitely tell me that is a constant. If I give you exactly this one and I ask you what is the function whose derivative is this, probably you immediately answer that by using this table. More or less, we want to do the same thing, but we want to adapt the table that I want to complete now in a way that is more suitable for primitive functions rather than taking derivatives. Yes? So I will explain that. But before that, let me define what do I mean by a primitive function. So that is good to define it here. So definition. And this is a standard notation. We say that a function, we denote it by capital F. A function f is said to be a primitive function of little f if, when I take the derivative, when I differentiate capital F, it gives me little f. If this happens, I would say that this capital F is a primitive function for the little f. Yes? Let me give you an example. Example. Both functions so let me call one of them capital F number 1 f of x equals to x squared, and f2 of x equals to x squared plus 5 are primitive functions of the function f of x equals to 2x. Since, why is that? Because if I take the derivative of capital F1x, what is the derivative of this? Is 2x, which is equal to my little f of x. because the derivative of capital F1 of x is equal to the little f of x, I would say that f1 is a primitive function for that f. Yes? And the reason is that why the second one is also a primitive function, for the same reason. If I differentiate the second one, even though this function is different from this function by this additive constant 5, but it doesn't matter when it comes to differentiation, because when I differentiate this, the derivative of x squared is still 2x, the derivative of 5 is 0, and it doesn't play any role. So you see that the derivative of f1 and f2 are both equal to 2x, and both are equal to the little f of x. So this tells me that I can consider capital F1 and capital F2 both as primitive functions for the function little f of x. Yes, is that understandable? Yes or no? Okay. But then I hope that you immediately agree that if I ask you how many primitive functions you can imagine for this little f of x, how many of them are there? There are infinitely many. So instead of adding 5, I could have added, I could have added, for example, minus 7. But the derivative of that one is still 2x. So it is clear that if I give you one primitive function, if you can find one primitive function, you can immediately find infinitely many primitive functions by just adding a constant to the functions that you have already found. Yes? Is that clear? Okay. But the point is that the other way around is also true, but the proof is beyond the scope of high school. It's not trivial. So this one is trivial. If I give you a function, a primitive function, and if you add a constant number to it, it is clear that the new function is still a primitive function. But the other way around is not trivial. Meaning that if you have two primitive functions for the same function, they differ only by an additive constant. It is not trivial, but it is true. So you need to have my words on it. Okay, so let us just write this one. So remark. So let me write it in two ways, yes? Number one, if f is a primitive function for little f, then f plus a constant c is also a primitive function for little f. For every constant c. Yes, this is something that you can prove at the level of high school. It's very, very simple. This means that, what is the meaning of this sentence? F is a primitive function for little f. All this part of this sentence means f prime is f. That is the meaning of this sentence translated into mathematical symbols. Then my claim is that f plus any constant that you like is still a primitive function. So what I have to show? I have to show that f plus c derivative is still little f. But that is clear because of this rule, addition rule here. You see, I can write it as the derivative of the first one plus the derivative of the second one. But the derivative of a constant, because of the first row in that table, is 0, so it becomes f prime. But if I ask you what is f prime, capital F prime is little f. So again, I turn back to f. So this means that this is done, yes? So if you give me a primitive function, and if I add one constant to your primitive function, I get, of course, a new function, but that function is still a primitive function. But I want to write the second one, I want you to know it, but the proof is not that trivial. You need a little bit more advanced theorem to be able to do that. So number two, if f, let us write capital F, let me write f1 and f2, capital F1 and f2 are both primitive functions for the same function little f, then if one of them is the other one plus a constant for some constant c. So in other words, if you have f1 prime equals to f2 prime, if you note that the derivative of two functions are equal, both of them are primitive functions for the same function. What does it mean? It means capital F prime 1 is little f, capital F2 prime is also little f. So it means that if the derivative of two functions are equal, you cannot be 100% sure that the functions are equal. But the point is that they cannot differ that much. That is the whole point. They can differ at most by an additive constant. Is that understandable? So this means that there exists a C in R such that one of them, for example, this is equal to the other one plus that constant. That is the meaning. I am not talking about the proof. The proof I told you is beyond the scope of this lesson, but I want you to know that. If the derivatives are equal, don't conclude that the functions are equal, but they are not that different. That is also true. They might be equal, but there is no guarantee for that. But then one of them is the other one plus at most an additive constant, not more than that. Yes? What does it mean, by the way? Can you tell me what happens if I tell you the derivative of a function is 0? Can you tell me what can I conclude from here? Yes? If the derivative of this one is 0, so I'm asking you, tell me a function whose derivative is equal to 0. Yes? It is a constant, yes? You cannot say that because the derivative of 0 is 0, because the derivative of f is equal to the derivative of 0, you cannot conclude that f of x is identically 0. But what you can conclude that there exists a C in R such that f of x is equal to that constant. Yes? So they are actually completely equivalent. If two derivatives are equal, they are not 100% equal, but they don't differ that much. At most, one of them is a constant plus the other one. And if the derivative is 0, probably this way is more trivial for you. If the derivative is equal to 0, the function that you are facing is a constant function. And this is, by the way, an important tool sometimes. Let me give you an example. Okay? We want to use this idea to prove this very famous trigonometric identity. So I would say that for all real numbers x, prove that, of course, what I write here is completely trivial for you, hopefully by now. Sine x squared plus cosine x squared is 1. So we learned about this in trigonometry, but let me tell you how we can use these ideas about primitive functions and things like that to prove this again in a different way. So if I want to prove this, what I do, I would say that let capital F of x be equals to sine squared x plus cosine squared x. I define a function for myself. Yes? And then I want you to do it for me. This you have to do. You should be able to do it at this stage. Yes? Can you calculate the derivative of this function? You might say why I should do the derivative. You need to be patient, wait and see why this is useful in this case. But can you tell me what is the derivative of this? I paused the video and I want to do this. I want you to do this yourself. This is at the level of the book and you should be able to do it based on the knowledge that you gained in the previous chapter. I give you 2 or 3 minutes. So for this one you also need the chain rule. So the chain rule, do you remember, was f of g of x. So if you don't mind, let me write the more applied version of the chain rule. Where are these? The applied version of the chain rule, do you remember, was f of u prime. F of u is a function of x prime, is f prime of u times u prime. Yes? So these are the only formulas that we have. Okay, any progress? What is the derivative of this function? Is it? You should dare to say what the number is.
I'm guessing 0.
Okay, so you're guessing. Yeah, your guess is correct. The derivative is 0. Yes? You should be able to guess it immediately, by the way, because you know that this is 1 and the derivative of 1 is 0. But not in this case, because now I am not taking this for granted. I want to prove that, so I cannot rely on that. But of course, I cannot have discrepancies, yes? But let us learn how to differentiate this. I don't know, let me repeat this one. If I want to differentiate, let me write this because I think some of you are still missing that. So I take the derivative of this. Then the first rule that I have to apply is the addition rule. So this becomes the derivative of the first one plus the derivative of the second one, yes? But what rule I need right now, I do not have sine squared in my table. I only have sine x. I do not have cosine squared in my table. I have only cosine x. So this means that I have to use the chain rule somehow. And hopefully, for this one, I need one chain rule. For that one, I need another chain rule. For this one, I hope that you agree with me, taking this to be u is a good idea. Yes? So what is the derivative of, let me write it here, u squared prime, according to the chain rule, is 2u. You can pretend that u is x. X squared is 2x, u squared becomes 2u, but because u is a function of x, you have to remember to multiply by u prime. And I will do the same thing for cosine, yes? So what I will do, let me continue here. 2u u prime. So it becomes 2 sine x, but it is not finished, multiplied by sine x prime. And then I go here. But here I take this one to be u, but the rule is the same. So it becomes plus 2u, which is 2 cosine x, multiplied by u prime, cosine x prime. This is not finished yet because still I have prime left, but that is easy now. Because sine x is exactly, you see it in the table, and cosine x exactly, you see it in the table. So what I can do, I can write 2 sine x. The derivative of the cosine, the derivative of the sine, according to the table, is cosine. But the derivative of cosine is negative sine. So this becomes negative now. 2 cosine x sine x. Yes? So I used two chain rules, one for this, one for that, and then I used the table of derivatives. And then I got this one. But 2 sine x cosine x is exactly the same as 2 cosine x sine x. One of them positive, the other one is negative. So it means that the derivative is 0. Okay, is that understandable? So I was able to show that the derivative of this function is 0. So according to this remark, it means that my function is a constant value, is a constant function. So what does it mean? Therefore, yes, therefore, what we have is this. Therefore, sine squared x plus cosine squared x is a constant. Okay, but we are not done yet, because of course this is a good progress. I realize that this is a constant, it cannot change. But what constant it is also important for me. I want to prove that this constant is exactly 1, not any constant, exactly 1. How can I motivate that this c should be 1? Yes?
Can you take a value for it?
Exactly. Because this claims that the left-hand side does not depend on x. Apparently it does, because you see x there. But according to this has to be a constant. When it is a constant, it is independent of the choice of x. That is the meaning of being constant. So it means that to understand the value for c, you can calculate the left-hand side for any value of x that you can, and it is simple for you. Whatever you get is that c. Do you understand the logic? Because we know that this expression is supposed to be a constant. It means that every value that I choose for x gives me the same value c. And I want to find c. So it means that I can choose x, any number that I can calculate the left-hand side easily. Probably the best choice is to take x equals to 0. And then this means that sine squared 0 plus cosine squared 0 is supposed to be my constant c that I'm looking for. But sine of 0 is 0, cosine of 0 is 1. So then the left-hand side, this means that 0 to power 2 plus 1 to power 2 is c, but that means that c is indeed 1. So you see, the first step is to show that this is indeed a constant. And the second step tells you that, okay, now that this is a constant, it doesn't matter at which number I am calculating it. I just calculated at some point, and I got that c is equal to 1. Then I put this c back here, and that would be another proof for this based on that remark. I want you to understand this logic. That is actually an important tool sometimes for proving that functions are constants. Yes? Okay, anyway. Now, the whole point of today's lesson is to try to reverse this table. Okay, but I want to reverse it. I could, in principle, write 0 here. You can write c here. Yes? So you see, the little f, capital F is the primitive function of that. Why this is true, you take the derivative of the right-hand column, the answer should be what is on the left-hand column. Yes? So that is true. Of course, I can write this in this form. Yes? Oh, sorry. Yes, I can write it in this form. That is correct. But this is a little bit strange, yes? Because I am telling you, if you have this combination, the primitive function is this. So it means that your exponent should be something minus 1. So this is a little bit strange. This is why I want to adapt myself with the new concept, okay? So what I write is this. X to the power of c. I want you to guess a function whose derivative is this. Can you guess that? What is the function here? I want you to guess a function so that when I differentiate, it becomes this. For example, if I give you x and I ask you, guess a function whose derivative is x. What is that function? Yes?
X to the power 2 divided by 2.
Yes, because if you just say x to the power of 2, it is good, because if I take the derivative of this one, 2 goes down, it becomes 2x. It is similar to this, unless because of that 2 I have to get rid of that 2. So what I do, I divide it by 2. Now everything is okay. If I ask you to differentiate this, you don't care about this one for differentiation. You take the derivative of this one, which becomes 2x. but the 2 coming down, I compensate for that by multiplying it by 1/2 and I get that. Yes? And I ask you, can you tell me a function whose derivative is x squared? X to the power of 3 is a good choice, because if I differentiate it, it becomes 3x squared. It's not exactly this, but I can fix that coefficient by multiplying it by 1/3. This multiplication by 1/3 will actually solve my problem, yes? Because now when 3 goes down, that 3 goes down, it will cancel this one, I will get this one. So this is why it's, hopefully you understand that I can do it like this. I can write 1 over c plus 1, x to the power of c plus 1, and of course plus a constant. Let me call it capital C. I want you to differentiate between this little c and this capital C. This capital C is always there, yes? If you want to find all of them. I will talk about that one as well. Is that understandable? Yes or no? Okay, but the point is that we had something in matrix C, we couldn't solve it. This formula has one weakness. Can you see the weakness in this formula? So I cannot apply that formula for one particular case, and we couldn't solve it in matrix C. So which number makes problem for me here? Which number for C makes this formula problematic? -1. So if C is -1, the denominator vanishes. Yes? But now you can solve the problem yourself. Yes? So let me ask you. Let me choose C equals to -1. We couldn't solve that case in matrix C. So now instead of C, I put x to the power of -1. Now I am asking you, can you give me a function so that when I differentiate it, it becomes x to the power of -1? Make sure that you understand this point. This is completely new lesson. You cannot use that formula because this formula does not make sense if C is equal to -1. So let me emphasize that. Okay, so can you tell me what that question mark is? You are thinking about a function whose derivative becomes x to the power of -1. You have it on that table, yes? You just need to look closer. What is that function? ln of absolute value of x, yes? You see here, x minus 1 has another better name. What is the other name for x to the power of -1? This is equal to 1 over x. Now I am asking you, give me a function so that when I differentiate it, it becomes 1 over x. But you have it here. This is the function, yes? If I differentiate this function, it becomes this. So the derivative, so the primitive function for this case is completely different. It becomes a logarithmic function. Yes? So I want you to write this one as well. So what happens, let me just move it up. What happens if c is equal to -1? So it means that if I give you this, so for c, so this is actually c equals to -1, yes? This becomes 1 over x, but the answer becomes totally different. It is not a polynomial function anymore. It is a logarithmic function. But of course, plus a constant c. Yes? Understandable or not? So, this is now completely solved. This formula is very good for all cases except -1, and the formula for -1, we got it this year. And that's the logarithmic function, the natural logarithm, yes? And then it means that we are done. We can solve the primitive function for this in all cases. Yes? Okay. But before continuing this table, I want to see what can I write for similar to these formulas for primitive functions. Unfortunately, there is no symbol used in the book for primitive functions, and they are not probably talking about that much, but that is extremely important. Yes, they are actually not even referring to that. So we have to invent a new notation, because the notation in other mathematics books is just the integral. But they want to avoid this symbol, and I understand why. Yes, let us stick to the conventions in the book. So you do not have this. If whenever you have this symbol, you have a number here and a number there. That is called integral. But if you go to a university text, this is called definite integral. If I take this one, out, that is called the indefinite integral. Yes, so for the time being, let us stick to the convention in the book. I want to write something similar to these rules, if there is any of these kinds, for primitive functions. Okay, the first thing, let me use this acronym PRM. That is just my own invention. That is not universally adopted, but let us just use this. If I ask you, find a primitive function for C times F. So it means that you have a function, you multiply it by a constant, and you want to find a primitive function for that. That is exactly analog to this graph, this formula. This becomes exactly the same thing. You just calculate the primitive function of your function, whatever it is, you multiply it by C. So this rule is in correspondence with that rule. We have also a similar rule for primitive functions like that. I can call it addition rule. So this means that primitive function of a function f plus another function g, it becomes equal to the primitive function of the first one plus the primitive function of the second. And the same is true for negative, for subtraction. So I have analog of this one. But there is no analog for the product rule. There is an analog. It's called integration by parts. Might be we will study a little bit of that in Math 5, but not in Math 4. Okay? So we do not have a very simple formula for the primitive function of the product. So what I want to emphasize, I want to write it and cross it over. Okay? Don't think that the primitive function for f dot g is equal to the primitive function of f multiplied by the primitive function by g, or even you might think that using this idea, the primitive function of f times g is the primitive function of f multiplied by g itself plus the other way around. No, none of them are correct. So we do not have any simple product rule for primitive functions. We do not have any simple rule for the quotient rule for the primitive functions. You cannot write this. So you remember, so if you even go to higher text, you will not see any formulas for the primitive function of the product and the primitive function for the quotient. We don't have those rules. But we have these rules, yes? Okay, now let us do some practice for these functions that we have so far. This is more or less a repetition from Math 3C, but of course in this case we have one more formula that I can use. In Math 3C we couldn't use that, yes? So let me give an example. Example here. Okay, let me, by the way, tell you something about these words. We can have a primitive function this article A, we can say all primitive functions we can also talk about the primitive function. So I want you to understand the differences here, here, and there. Okay, so if I ask you to find all primitive functions, it means that you need to show respect to the fact that you have to put this constant there. Yes? So it means that I want you not to find one of them, but all of them. So it means that when I use this all, it means that I am asking you to show me that you understand that you have to add a constant at the end. Yes? Because I want all of them, not just one of them. But if I ask you a primitive function, you can choose any number that you like for C, but of course, which one is the simplest choice? Is 0. Yes? So when I say a primitive function, you can immediately forget about this constant C. If someone asks you why there is no C, you can say that I chose C to be 0. Of course, you could choose C equal to B equal to 1 or any number, but the simplest choice is 0. So when you say a primitive function, forget about writing this C. And when I say all primitive functions, you have to show me that you write this c at the end. The primitive function, we will come back to this later. It means that there should be a unique primitive function, but this, you need an extra piece of information in the problem itself. But at least I want you to appreciate the differences between these particles and atoms. Okay, this example is important, not because it is hard, because I want you to understand what is going on. So determine primitive functions. So let me write all primitive functions, okay? Determine all primitive functions for each given function below. Yes? So number one. So f of x is equal to 5x squared plus 3x square root of x minus 2. I don't want to spend some time on very, very simple examples. If you need more simpler examples, you can refer to the videos of Math 3C from last year, because this year we haven't reached to this topic yet. Okay, so I want to find a primitive function for this. How should I do that? I need to reform exactly the tricks that you learned for derivatives also works here. So here, this function, I don't have any problems with that one, because this is similar here. And this constant is not a problem for me. I can just pull it out. But then you see that I do not have a product rule. That's a product between these two functions. And I do not have any product rule for primitive functions. So it means that I have to change the form of this function. So what I write with blue is actually the solution. So the first thing that you have to do, you have to adjust yourself with the table. That table and that table, both of them will be given to you in the exam. Okay? So you need to adjust yourself with the table. So this one, I don't do anything with this one. But then hopefully you remember the tricks from before. There is another name for a square root of x, and that is x to the power of 1/2. But there is also another x here, which is supposed to be multiplied here. So what I will write plus 3 x to the power of 1 multiplied by x to the power of 1/2. It becomes x to the power of these two numbers added, which becomes 3/2. Yes? And then I have minus 2. Now it is ready, so I can write capital F of x is equal to 5 is a constant, is a multiplicative constant, so don't do anything with that and try to solve the problem here. X to the power of 2, I use this formula. C is 2. So what is the answer? It becomes 1 over 2 plus 1. And please do not write these details. It would be very boring if you want to write all the details. But let me write it once. And then here, plus 3. And the same thing happens here. But now this number playing the role of C. So then what happens? I would write 1 over, I am using that formula, the second row. Yes? It becomes 3 over 2 plus 1, and then x to the power of 3 over 2 plus 1. So what happens for minus 2? What is the derivative of minus 2? What is the function whose derivative is minus 2? 2x, yes? By the way, that is also this formula. So let me write this explicitly for you, even though I don't remember is it in the formula sheet or not. But remember, let me add something here with a different color. So here, if I choose a constant here, not 0, what will happen? If this is 0, that is a constant. But if this is another constant, let me also write that one as well here. So if I have a constant here, okay, if I have a constant c, the answer is cx.
Why is that? Because if I ask you to differentiate this function, you definitely get C. But if I want to write all of them, I need to add capital C as well. So if you have 0, of course you don't need to have two formulas, yes? Because if you have this formula, it also covers that one. So anyway, if you have 0, that is simply a constant. If you have another constant, not necessarily 0, the answer is Cx plus a constant. So here, the answer to -2 is -2x. But because I have asked for all primitive functions, you have to respect and write a capital C at the end. And here I really expect you to be able to simplify these numbers. So let us do it quickly. 2 plus 1 is 3, so it's 5 over 3, x to the power of 3. Okay, so let us do this one here. Can you do it in your head? What's the answer? 3 over 2 plus 1 is 5 over 2. But you have the reciprocal, it becomes 2 over 5. 2 and 3 will be multiplied, it becomes 6. So it becomes 6 over 5. X to the power of 3 over 2 plus 1 is 5 over 2. And then minus 2x plus a constant. Yes? So that is the primitive, all primitive functions for that function. It means that no one else can find any other answer except this answer for a primitive function for this function. Okay, let me add one more example at least. Yes? So, number 2, I give you this function, f of x is 5x to the power of 3 plus 2x squared plus, no, let me make it minus here. So let me put the denominator first. So you have 5x cubed, let me write it here, and then I will write plus or minus square root of x. Let me also make it 3. So you want to find a primitive function here. By the way, if you see I ask you to guess a function whose derivative is this one, you might think that you are guessing all the time, but it is not the case. If I ask you, find a function whose derivative is this one, there is no guessing going on. This is so complicated that we cannot guess a function whose derivative is this one. So even though somehow I ask you to guess a function whose derivative is this one, you might consider this a guesswork, but of course after guessing, I motivated you why this works, because you take the derivative of this one and confirm that this is indeed the case. But you might say that somehow we guessed. But I hope that you agree with me, there is no way to guess a function whose derivative is this one. We have to calculate. So we are getting powers out of it, yes? So how should I do that? The tricks are very similar to the tricks for the derivatives at this level. So if I give you this function to differentiate, what was the idea? Of course, at this stage, you can use the quotient rule. But I told you that even if you now know the quotient rule, this is not the most efficient way to do it. The most efficient way is to divide this by this by that, and this by that. Yes? For the primitive function, this is the only way, because there is no quotient rules for primitive functions. That's the only choice. So what I have to do, I write in blue. Okay, so what I want to do, I want to change it to a form that I can use my table of integration, my table of primitive functions. So the first thing that I do is to write this. This one divided by that one separately, and then this one divided by that one, and then this one divided by that. So you don't have any problems here. It becomes just simply 1. But in differentiation, do you remember we took everything upstairs? But here you have to be careful. Most of the time you do this except for one exception. If I simplify that, it becomes 1 over x. For derivative, you even move 1 over x up, you write it x to the power of minus 1. But here you have to respect this rule, that this general rule does not work for one special case. And that special case is that if you have 1 over x. So if you have 1 over x, you have to keep it 1 over x. So I have 2 over 5. x2 and x3 are simplified. I am left with 1 over x. But then this I have to simplify. How should I simplify that? Another name for this is x to the power of 1/3. And then I am dividing. So what I do, I bring it up. So it becomes x to the power of 1/3 minus 3. But then I can write it x to the power of minus 8 over 3. 1/3 minus 1 minus 3 is minus 8 over 3. And then I have a 1 over 5 here, x to the power of minus 8 over 3. So the only exception, I didn't take this one up because for integration I have a separate formula for the case of 1 over x. This is the only thing that you have to be careful in this case. And then everything is ready, yes? So now I can write all primitive functions f of x is equal to a primitive function for 1 according to this red line here is that number times x. This one is 2 over 5, but the derivative, the primitive function for this is the third line here. So it is ln of absolute value of x. And by the way, in this lesson, if you do not write absolute value, just write x, that is okay as well. But then you need to remember that only works for positive values, yes? And then here, I have minus 1 over 5, and then for this one, I have to use this rule. So what is the answer? It becomes x to the power of minus 8, so let me write it in this form. It is 1 over minus 8 over 3 plus 1, x to the power of minus 8 over 3 plus 1, and then I will write a constant at the end. Because I am asking you to find all primitive functions. But then you simplify it a little bit. So f of x is equal to x, 2/5 ln of absolute value of x. Then if I calculate, let us calculate this in our head. So this becomes minus 5 over 3. So that minus will cancel this minus. It becomes positive. And then 3 goes up. 1 5 is left here, 1 5 comes from here, multiplied together is 25. And then if I simplify that, it becomes minus 5 over 3, and then plus a constant c. So that is the final answer for this problem. I hope that you agree with me. Guessing this one was not easy. So this means that even though we started somehow from guesswork, but we were still able to solve harder problems without guessing anything, which was not possible to guess. So is that understandable? So I would say that the only thing that you couldn't do in Math 3C level was you couldn't understand how to do this one. But the rest of it is a Math 3C lesson. Any questions? Okay. I want to complete this, yes, because the rest of it you can immediately conclude. But let me clean this. I want to clean this one to make this more transparent. So let me get rid of this. Yes. Yeah, I can wait a little bit for you so that you can write your thing. And then let me remove this one not to interfere from here. Yes, because I already emphasized that C should be positive and not equal to 1. Okay. Now we want to talk about the rest of this table. Sine, cosine, and tangent. Okay? So how should I do that? I want to ask your help with that. Oh, sorry. We still have these exponential functions here. Okay, so if I ask you, give me a function whose derivative is this one. So I write e to power cx here, and I want you to give me a function whose derivative is this one. And I can write the same thing here for c to power x. Give me a function whose derivative is this. Give me a function whose derivative is sine cx. Give me a function whose derivative is cosine cx. Yes? For the tangent, I will explain a little bit later. Okay, so now we want to complete these things. So these two you studied in Math 3C. These two you studied actually this year because we didn't know about the derivatives before. Okay, can you tell me what happens here? What is the function? You should be able to guess a little bit, and after that you can prove your guess. What is a function whose derivative becomes this when you see that the derivative follows this rule? For example, can I write e to power cx? Not exactly, because if I differentiate this function, according to this rule, I get an extra c here. But I have to compensate for that extra c. So what should I do? I have to divide by that c. And because I want all of them, I can add a capital constant c. Yes? If I ask you about this, you can write c to power x. Yes? If I ask you to differentiate it, what you get? You get this one, that is correct. But you get an extra factor of ln of c. You want to get rid of that. So you have to divide by that. Okay, can you also guess these two for me? Can you give me a function whose derivative is sine cx? So I hope that you agree that this should be somehow cosine function, yes? So cosine, if I write cosine cx, do you agree that it is more or less good, but I need to fine-tune it a little bit, yes? If I ask you what is the derivative of cosine cx, what is your answer? So what is the derivative of cosine cx? That is previous chapter. What is the derivative of cosine of cx? The derivative of cosine is sine. Oh, sorry, minus sine. So first of all, you agree, hopefully you agree that this is minus sine cx, because I have to take this one to be u in my head. Cosine of u prime is negative sine of u, but it is not finished. I have to multiply by the derivative of u. But the derivative of this is minus c sine cx. So the derivative of cosine cx is minus c sine cx. So that is not a good answer. Because if you write this and you differentiate this function, you do not get exactly this. You get a factor of minus c out. You have to compensate for this factor, so you divide by 1 minus c here. Minus 1 over c. So don't get confused. In the derivative of sine is positive cosine, but the primitive function of sine becomes negative cosine somehow. And then I have a constant c here. Immediately you can convince yourself that this one is 1 over c sine cx. Okay, so when we studied these things very close together, might be you get a little bit confused, but you don't need to be worried, yes? This table you will get it, this table you also get it. But you need to understand, the first table is useful when you want to find derivatives. The second table is useful when you want to find primitive functions. Some of them are very close and similar together, but you don't need to be worried about that, because the tables are in front of you. The only thing that you need to know is that this table is useful when you want to do primitive functions. This table is useful when you want to do the derivatives. Okay, so that's very, very simple in that case. Okay, so let me give you some examples. Okay, so let us just write the functions here. I want to find all primitive functions. So let me give you some of those examples. For example, I give you this function, f of x equals to, let us say, e to power 2x plus e to power minus 2x to the power of 2. I want to find all primitive functions for this function. Of course, somehow you understand that this formula should be somehow useful. But the point is that that function is not exactly this function. I have to change the form of that function so that I can use this. So what is the idea? Hopefully you agree with me, squaring it is a good idea. So what I do, the first thing I have to do is to raise it to power 2. This one to power 2, it becomes e to power 4x. 2 times the first one times the second one. And then the second one to power 2. But there is something that I can do for this case. What is the answer to this? It's 1. Yes? E to the power of 2x multiplied by e to the power of minus 2x is 1. Multiplied by 2 is simply 2. So let me write it a little bit organized form. This I write first. That I write second. Then I will write that 1 times 2, which is 2. Now everything is ready to find a primitive function. Yes? This one and that one are both these formulas. This formula. So how should I do that? All primitive functions, capital F of x is equal to. A primitive function for this is 1 over 4 e to power 4x. Here, 4 is playing the role of that c. This one, minus 4, is playing the role of that c. So it becomes plus 1 over minus 4. And then e to the power of minus 4x. For 2, I have to use this red line here. Yes. So the answer becomes 2x. But of course, because I have asked for all primitive functions, you have to add this constant c at the end. So that would be a primitive function for this. Okay, so we can also solve some trigonometric problems. So let me give you this function. F of x equals to 5 sine 3x plus 2 cosine 3x over 5. We want to find a primitive functions for that function. Okay, so immediately you can compare, yes? I hope that you agree with me. For this formula, for this one, this formula is useful. For this one, probably this formula would be useful. But let me rearrange it a little bit. So it becomes f of x is equal to, this I don't need to do some rearrangement, so let me just write it as it is. If you don't mind, let me put it in pair of brackets. And then here, I can write it as 2 cosine. Instead of 3x over 5, I write it in this 4, which is exactly the same thing, but written in a way that I can read the coefficient easily. Yes? And now, for this one, this is playing the role of your c in this formula. For this one, this is playing the role of your c in this formula. Okay, so what I have to do, I have to write 5, but for this part, I use that formula. It is minus 1 over c cosine 3x. But then I have a 2. For cosine cx, I use this formula. It is 1 over c. This is my c. 1 over c becomes that. And then it becomes sine of 3, 5x. And then, of course, I will have a constant c at the end. But let us simplify this a little bit. By the way, so this equality is wrong. I have to write capital F of x is equal to. So then it becomes minus 5 over 3 cosine 3x. And then 3 over 5 goes up. It becomes 10 over 3 sine 3x over 5. and finally plus a constant. Yes? One more example and then we are done. So what do you think about this function? Because I told you that there are no product rules, so you need to somehow find a way to solve this one. So sine x multiplied by cosine x. So if I ask you find all primitive functions for this function, do you have any idea what to do? That would be the last example for today. I think I see it in the book, this is why. Yes, that is level 2 problem, the last one I think. Yes. So how should I do that? Because of course sine x is in my table, cosine is also in my table, but I know that for primitive functions, in contrary to the derivatives, we do not have any formula for the product rule. So it means that I cannot say the derivative of this one, primitive function of this multiplied by that. Yes?
Use the double angle.
Double angle. That's the trick. So what you need to do, you need to write 1 over 2 sine 2x. Because this combination I told you when I was teaching you trigonometry, this should look familiar to your eyes. The product of sine and cosine of the same angle, it's 1/2 of the sine of the double angle. And then everything is done. So instead of thinking about this problem, you can think about this problem. But you see 1 over 2 doesn't make any problem for me. So just copy and paste it. And this part, I can use this row of the table, yes? So it is minus 1 over c. This number is playing the role of my c now. And then it becomes cosine 2x and plus a constant. This times that, it becomes minus 1 over 4 cosine 2x plus a constant c. Yes, any questions? Okay, so we stop here and then yes, for the other group we have still one more session. So even though I asked, you also have one more session today, so no problems. Yeah, you can be even at that. Any questions? No? Okay, thank you.